Hello everyone, welcome to the next lecture of finite element analysis, and this lecture is only for the mechanical department and civil students don't have to watch this. So we are going to start unit 4 of finite element analysis, which is steady state heat transfer. So unit 4 is steady state heat transfer. So we have already studied this subject heat transfer in the previous semesters. So I'll quickly recapitulate what we have studied. So there are three modes of heat transfer. The first mode of heat transfer is conduction, then the second mode is convection, and the third mode is radiation. The conduction heat transfer is through solids, the convective heat transfer is through fluids, and the radiative heat transfer is through electromagnetic waves. Again, the conductive heat transfer is governed by this equation, which is Q is equals to Ka into dt by dx. So in conduction we have this term K, which is called as thermal conductivity, which we have already studied in heat transfer. And then the second equation is this equation for convective heat transfer, HA delta T. So this term will be given for convection. So this is convection and this is conduction. So in conduction, thermal conductivity will be given. In convection, heat transfer coefficient will be given. This is also called as convective heat transfer coefficient. So what is the unit of thermal conductivity? So it could be watt per meter Kelvin or watt per meter degree centigrade or watt per centimeter degree Kelvin. So these are the units of thermal conductivity, whereas for heat transfer coefficient you have watt per meter square degree centigrade or watt per centimeter square, whatever it may be, degree Kelvin, whatever it may be. So next, the last mode of heat transfer is radiative heat transfer, and the formula is given by Stefan Boltzmann's law, which is F sigma A into T1 power 4 minus T2 power 4. So these are the three formulas for steady state heat transfer. Again, for unsteady state, the time will come into consideration, but in finite element analysis, we have only steady state heat transfer. We used to make use of these formulas for solving problems of heat transfer, but in finite element analysis, we have to make use of matrix forms, because in the systems where FE softwares are used, where finite element softwares are used, the data will be input in the form of a matrix. So we have formulas in terms of matrices here, and all these thing can be, you don't have to calculate it manually. If you give the input values to the software, like if you are giving input values of temperature in ANSYS software, the ANSYS software will help us in determining the temperature at every point of that member. For instance, let's take, you have one example here. Let's take, you are performing analysis of this wall. So this wall is a solid wall, so it has some thermal conductivity K value. So this thermal conductivity K value is the input value which you have to give, and this depends on the material of this wall. So for every material you have different value of thermal conductivity K. So that will be your input value to the software. And again, let's say you have some convection load here, something kept here, some fluid is kept over here, so you have some H. So H for convection load, you should give what is the thermal convective coefficient of that fluid and the temperature of that fluid. Okay, and let's say you have some more fluid here, and let's say you have some hot fluid, and you have, let's say this is H1 and TF1, and this is H2 and TF2, HF2. Okay, so we have, let's say we have to find out the temperature at this point. So we can determine this temperature by giving all these values, and we have to perform, we can perform this type of analysis using any FE software. So we are going to write down some set of formulas of such conduction, convection and radiation in finite element analysis. So the Fe equation now changes. Till now we have been using K into U is equals to F as our finite element equation. Now the finite element equation is K into T is equals to F, because now we have to find out temperature. Temperature, T stands for temperature. K here is conductance plus convective matrix, conduction plus convection matrix. T is temperature, F is force. Okay. The second formula is, what is this conduction and convection matrices? So conduction matrix formula is quite similar to the formulas which we have studied earlier. So K is equals to small k. So there is a difference between this K and this K. So this is thermal conductivity and this is conduction matrix. So K into A by L, 1 minus 1 minus 1 1. So earlier we had E into A by L, 1 minus 1 minus 1 1. That was for bar problems, and we have this conduction matrix K is equals to K into A by L, 1 minus 1 minus 1 1. Again for convection matrix, K is equals to H into A by L, 1 0 0 1. Now this formula changes from problem to problem. Let's say this is a 2 by 2 matrix which indicates 2 points of an element. Consider this example. There are 2 points, point 1 and point 2. And let's say you have some fluid here at point 2. Some H fluid which has a temperature of some F. But we don't have any fluid at point 1. So this matrix will be for entire element. So that is 1, 2, 1, 2. So if you see this formula, even though there is no H here, the H is getting multiplied at the node 1. So in such cases, what we have to do is, since there is no H load, at node 1, we have to change this formula to this way, 0, 0, 0, 1. Because there is no convective load on node 1. The H load which is convective load is only on node 2. So at node 1, this value will become 0. Similarly, if we have only H load at node 1 but not at node 2, so this is H, so this is node 1 and this is node 2. So the H load is only at node 1. So in these cases we have HA 1 0 0 0. So this is for node 1. At node 2 there is no H load, so we will have to make it 0. So this formula will depend on the type of problem we have. So the next is we got K, T we have to determine. Next is the force matrix. So the force matrix, the first force is convective load or convective force. The second one is flux load Q. So this will be given in terms of Q. And the third force is convective load in lateral direction. What do you mean by convective load in lateral? This convective load is in linear direction and this convective load is in lateral direction. What do you mean by linear and lateral direction? So this is my wall. Let's say I have to find out some convection is there here. So how much this temperature will flow in the linear direction? Okay. So how the temperature distribution will be along the same line. And if we have the same case and the load is on this sides, the lateral sides, and I have to determine the temperatures in this direction. So in this case we have to make use of this formula. So this formula will be usually found in fin problems, and we are going to solve those fin problems. So convective load is HAT11. Again, this thing will change inside the matrix depending on the problem to problem, and I am going to explain how this is going to change when we solve problems. The next formula is QA11. Again, this values 1 and 1 depends on the case to case. And the last is HPT L by 2 1 1. So these are the temperature of fluids. So I am going to write this TF and TF. Because of fluid we have convective heat transfer H. So because of fluid we have convective heat transfer H. So these are the different formulas, only 3 formulas to solve any problem on steady state heat transfer. The first formula is K into T is equals to F. So for which we have to determine K. So K can be conduction plus convection. So if there is no convection, we don't have to make use of this formula. If there is only conduction, we can make use of this formula. If both are there, we have to add up these values and we have to substitute here. Similarly for force, we can have all these cases together, or we can have one of these cases. So depends on problem to problem when we have to take convective load, flux load and convective load in the question, in the problem. So once we get this K and once we get this F, we can substitute K and F here, so we can determine the value of T, the temperature at every node. So I am going to solve the first problem. The first question here, for the nodal temperatures in a composite wall shown in figure, the wall is maintained at 100 degrees centigrade at the left face and convection mode of heat transfer occurs between right face and existing fluid. So this diagram has been given in the question. So the temperature here is 100 degrees centigrade, which is given, and on the right face this fluid is there, which has H and some temperature of fluid is there. So these values are also given in the question. K1 value is given as 0.06 watt per centimeter degree centigrade. K2 value is given as 0.2 watt per centimeter degree centigrade. The thermal H value is given. H is given as 0.1 watt per centimeter square degree centigrade, and the temperature of fluid is given 25 degrees centigrade. Area is given as 1 centimeter square. Okay, so this is the given data. So we have to determine the nodal temperatures in a composite wall. So if you see, there are two elements of this composite wall. This is my element 1 and this is my element 2. So the element 1 is connecting nodes 1 and 2, and element 2 is connecting nodes 2 and 3. So there are two elements. Element 1 is connecting 1 and 2, element 2 is connecting 2 and 3. So what is the given data? So this element is made up of a different material which has a thermal conductivity K1, whose value has been given in the question. Element 2 is made up of some different material, so it has some different thermal conductivity K, so K2 value has been given in the question. On the right side of this wall, this is a composite wall because it is made up of two different materials, and the left face of this wall is maintained at a temperature of 100 degrees centigrade. So we have to determine what is the temperature at this point T2 and what is the temperature at this point T3, and also on the right side of this wall there is some fluid kept whose H value, whose heat transfer coefficient value is given in the question as 0.1 watt per centimeter square degree centigrade, and the temperature of this fluid which is on the right side of this wall is 25 degrees centigrade. The area of the entire wall is 1 centimeter square. So this is the cross section area. So it will be same for element 1 and element 2. The cross section will be same for both the elements because separate areas has not been given. So it is the same area for element 1 and element 2. So the first thing is to, what is our finite element equation? K into T is equals to F. So we have to determine K. So for K, there are two formulas. One is for conduction and one is for convection. So conduction matrix for element 1. So for element 1, conduction matrix Ka by L 1 minus 1 minus 1 1. So everything is given in terms of centimeters, so we don't have to convert anything. Okay, so we can directly substitute here. So K value for element 1 is given as, so for element 1 we have to write down 1 1 1. So length, this is my length of element 1, this is my length of element 2. Okay, so K1 A1 by L1. So K1 is given in the question 0.06. A1 is given, since A1 and A2 both are same, so A1 is 1, L1 is 2 centimeters, so 2, so 1 minus 1 minus 1 1. So you can find out this value in the calculator. Yep, so we can find out this value in the calculator. So 0.06 into 1 divided by 2. So this is 0.03, 1 minus 1 minus 1 1. So this will be 0.03 minus 0.03, 0 minus 0.03, 0.03. So this is for nodes 1 and 2. So there is no convection. For element 1 there is no convection, there is only conduction. So here we can write down for element 1, since it is connecting nodes 1 and 2, so 1 2 1 2. Because there is no convection for element 1, so we have not taken the convection matrix into consideration for element 1. If you see element 2 has conduction because it is a solid, and on the right side of element 2 we have convection also. Okay, so here for conduction plus convection matrix for element 2, because element 2 has H on the right side which is fluid. So whenever we have H, that means we have some fluid there. The temperature of that fluid is also given. So the conduction formula is for element 2, K2 will be there now. So which is conduction. Conduction is Ka by L, 1 minus 1 minus 1 1. So for element 2 we have to write down K2 A2 L2. Similarly, we have the formula of convection, HA is equals to 1 0 0 1. But if we see element 2, for element 2 there is no convection on node 2. The convection is only on node 3. This H will affect only node 3. So the convection load is only on node 3. So this is element 2 which is connecting 2 and 3. Okay. So since we have only convection load on node 3, so the value on node 2 should become 0. So this should become 0 in the formula, because there is no convection on node 2. No convection on node 2. Okay. So now we have to substitute all these values. So we will get K2 is equals to K2 A2 by L2. So K2 is given in the question. So K2 is 0.2, area 2 is 1, by length of element 2 is 4 into 1 minus 1 minus 1 1 plus HA. So H value is given in the question. So H is 0.1 into area is given in the question. Area is 1 0 0 0 1. Okay, so we can find out this value in the calculator. So 0.2 into 1 by 4, this is 0.05. So this value is 0.05. So if I multiply it inside the matrix, 0.05 minus 0.05 minus 0.05 0.05. So this 0.1 into 1 is 0.1. So if we multiply that inside the matrix, that will become 0 0 0 0.1. So we can add up these two matrices. So we will get 0.05 minus 0.05 minus 0.05 0.05 0.15. So adding these two. So this is the value of K2. So now global K matrix. So K2 is connecting nodes 2 and 3. So nodes 2 and 3. K1 is connecting 1 and 2. So the order of the global matrix K will be, the global K matrix will be of 3 by 3 matrix, because it has 3 nodes. So it will have 3 columns and 3 rows. So at 1 and 1 we have this value 0.03, we have to assemble here 0.03 minus 0.03 minus 0.03 and 0.03. So we have assembled these values in the global K matrix formula. Similarly 2 3 2 3, if we assemble here, we are going to get plus 0.05 minus 0.05 minus 0.05 0.15, and the remaining values will be zeros. So we got K matrix. Next we have to find out force matrix F. So after getting K, we have to calculate the force matrix F. So there is only one type of force, which is convective force, which is acting on the right face of this element. So force has only convective force here. So the convective force formula is HATF11. But in this case, so this is on which element? On element 2. It is only on element 2. So for element 2, if we see HATF, this convective force is only on node 3 but not on node 2. So node 2 and 3. So for node 2 it is 0 and it is on only node 3. So this H value has been given in the question, that is 0.1. Area is given in the question 1. TF is given in the question 25, 0, 1. So 25 into 1 into 0.1. So that is 25 into 0.1. That is 2.5. So this is 0, 2.5. So it is connecting which nodes? So the total force, the force is, it is connecting 2 and 3. So the global force, because force matrix is a column matrix, so it will be 1, 2, 3. So at node 1 there is no value, at node 2 it is 0, at node 3 it is 2.5. So we got global force, we have got global K. Now we can substitute in this finite element equation, which is K into T is equals to F. So this is my K value. So K is 0.03 minus 0.03, 0 minus 0.03, this is 0.08, minus 0.05, minus 0.05, 0.150 into T. T will be T1, T2, T3, which is temperature at node 1, temperature at node 2 and temperature at node 3. Temperature at node 1, so we have taken that as T1, which is given in the question, and force is 0, 0, 2.5, 0, 0, 2.5. Now what is our boundary condition? The boundary condition is T1 value is given in the question. So boundary condition T1 is given as 100 degrees centigrade. So we don't have to consider this row. We are going to cancel this row because T1 value we have. Okay. So since T1 is 100, we don't have to consider this row. But what about these two values? Will it become 0? Because it won't become 0 because T1 is not 0 in this case. It has some value which is 100. So we can't multiply this matrix and this matrix. So in order to multiply this matrix and this matrix, now it has become 2 rows and 3 columns. And it has got only 1 row and 1 column and 2 rows. So we have to send these two values on the other side. So how we are going to send that? So now we have this matrix here 0.08 minus 0.05 minus 0.05, 0.15. So these two values has to be sent to the other side, 0, 2.5 plus, so this when I am sending it to the other side it becomes positive. So and this value is going to multiply with this value T1. So T1 is what value? T1 is 100, which has been given in the question. So when I am sending it to the right side, this into this goes to the right side, it becomes plus. So 0.03 into 100 and this 0 into 100 goes to the other side, it becomes 0. Okay. So now we can solve, here we have this T2 and T3 as well. T2, T3 is equals to. So now we can solve these two equations. So what are the two equations we have? 0.08 T2 minus 0.05 T3 is equals to this value, which is 0.03 into 100, that is 3, equation number 1, and the second equation is 0.05 T2 plus 0.15 T3 is equals to 2.5 plus 0 is 2.5, so we can find out these two values, that is T2 and T3, in the calculator. So go to the mode setup, select equation 5, select first type of equation, give the values 0.08 minus 0.05 3 minus 0.05 0.15 2.5. So the T2 value we got as 60.52 degrees centigrade and T3 is 36.84 degree centigrade. Okay, I hope you all have understood this problem, and if you have any doubts you can reach out to me. That's it for today. Thank you.